So thank you very much, Fabian, for the very nice introduction. So yes, indeed, I am an associate researcher at the TU Dresden, and yeah, I mostly work on issues related to the semantic variability of languages. Today, I'm going to be focusing on sample logics, which is a framework that we've been working on a lot. I started working on this on my PhD, and we recently have been working on the topic with more researchers, so it's pretty exciting for me. So today my pointer doesn't want to work. I think this has to do with the sharing of the screen. Oh, there we go. So I'm gonna try to. So first of all, I wanted to ask. I think I've already been talking to many of you, but I wanted to test a little bit how many have a logic background to adjust a little bit the presentation. So I would guess that everybody's familiar with logics to an extent, especially description logics.
I would say half of the team from
the university background of logics.
Totally fine. That's totally fine. So the idea here is I'm going to try to spend a fair amount of time giving you motivation for the framework and discussing a little bit the syntax and semantics. And I want to encourage everyone to stop me at any point and ask questions. So in a way, this is where I would like the message to come across. And then I'm going to go a little bit to explain what are the decidability and the complexity results that we've been publishing recently. So this is current work. It's a bit more of a technical nature, but perhaps we can reserve the details for specific questions if you have them. So in this area, we're going to be focusing on two specific fragments of first-order logic, which are sentential fragments and monodic fragments. To give you an early intuition, the sentential fragments are going to be easier and better behaved. They are going to be easier to implement as well. The monodic fragments, we go into more complex techniques to show the computational properties, but we still manage to preserve, for example, polynomiality for EL. And then I'm going to close with some conclusions and future work. I'm going to try to discuss some things that may connect with the team. So what about the motivation for sample logic? What we are going to look at is the semantic heterogeneity problem, but specifically with regards to knowledge integration. So this is something that everybody here is very familiar with. For example, I mean, of course, in the semantic web, we have a lot of different knowledge sources that come from different places, and very often what we are interested in is in managing to use them in an integrated way. So we're going to begin directly with an example. You can imagine that we are in the medical domain, and we have the SNOMED-CT, which probably you've heard of, is the largest ontology, the largest medical ontology in the world. And it will encode some background knowledge on medicine, okay? So it may encode something, among other things, that process and tissue are disjoint categories. Now, in first-order logic, we could encode it like this, with this axiom. I'm going to use first-order logics also in the introduction because I take it as a reasonably accessible language, but of course you can ask me. And then we are going to consider that there's two more knowledge bases coming into play, apart from the SNOMED-CT, that are going to be actually derivatives of this knowledge base. So they are going to be, for example, belonging to intelligent systems. We can have a hospital that collects data about patients, and this hospital models tumors as processes by which cells abnormally grow and multiply. So we may have these two axioms there for that. In addition, we may have another knowledge base, for example, from a laboratory, that models tumors as lumps of tissue, okay, because it just labels data from radiographies. Now, I can encode this in this way. And now, of course, very often, if we have these entities in the same country, they will want to share their data, they will want to make it interoperable, and we will have the typical challenges that we have in knowledge integration, okay? So a naive way to tackle this would be to try to put everything together to do some form of knowledge fusion, or ontology merging. And of course, this is not a trivial process, and it can lead to inconsistencies and unintended inferences, okay? So for example, if I have an object C that is a tumor, I'm gonna be able to infer with these axioms 2 and 3 that this is a process, with axioms 1 and 4 that this is not a process, and then I have an inconsistency, and that makes my knowledge base new. So the approach that we are following to deal with this problem in this talk is using standpoint logic. So the strategy here is going to be to represent knowledge relative to different points of view. Okay. So what I'm going to be doing is I'm going to use a modal logic with multiple modalities to be able to contextualize what are the perspectives behind the different axioms of my knowledge. So this is inspired by the supervaluationist theory of natural language. I'm not going to go in detail into this, but of course, if someone is curious, you can ask me later. But the idea here is that I'm going to have these box modalities, well, also diamond modalities, that are going to be labeled with standpoints. So for example, here I have S for the SNOMED standpoint, and I'm going to have P for the process standpoint and T for the tissue. So this is nice. Now, in addition to labeling these things, then the framework allows me to hierarchically organize these standpoints, to combine them, and to put them in relation to one another. So let's see how this works in practice. Here we have these axioms that we had before in the previous slide. And in addition, we may want to state that, in fact, both the process knowledge base and the tissue knowledge base, they were inheriting from the SNOMED CT, okay? They want to take all the axioms from SNOMED. So I can encode this with this sharper than operator that you have here, okay? There's a nice additional feature that you have in the line. But moreover, I'm gonna want to establish tighter relationships between the different standpoints, okay? So for example, I may know that whenever something is arguably a tumor, but it's also an object, okay, according to the SNOMED CT, then it must be, we must be talking about the tissue standpoint, okay? Because if it's an object, then it's definitely not going to be a process. I may have this axiom here stating that in this case, we are definitely going to be talking about the tissue standpoint. I may also have interactions between the two knowledge bases, okay? So for example, like this lab and this hospital, they may know that they roughly talk about the same thing. So for example, the hospital may know that whenever the hospital says that something is a product of a tumor process, then the lab will label that as a tissue, okay? As a tumor tissue. So I can encode this with this. And similarly, they may have like a very similar understanding of what the tissue is. So whenever the tissue standpoint says that something is a tissue, then that's also a tissue according to the process standpoint. So if now I have some instances, well, of course, this is not going to be inconsistent anymore like it was before. But moreover, we can actually reason with the whole thing, and we can transfer information across the two standpoints. So let us look at an example. Let us look at how this example builds up with these axioms. I'm going to try to show you a representation of a model. So this is a bit complex, but we're going to try. So on the top layer, we're going to have our domain of individuals here, okay? And on the side, we are going to have admissible interpretations, which you can think of them as possible worlds or specifications, we call them in supervaluationism. So I'm going to have my patient P1 here. This is the first instance that I have. And this is, here our modality is for the SNOMED CT in general. So this interpretation is going to belong to S, this interpretation pi. Okay, so I have my patient P1. This patient has a part in this interpretation. There is a tumor and an object. So here we have our tumor and object. Now, what we are going to be able to infer is that actually from axiom 6, we know that if something is a tumor in an object, according to S, then it's definitely a tumor according to T. So I know that in all the interpretations of T, this is actually going to be a tumor. So this is known. Moreover, I also know from axiom 4 that then every 2 more according to T is also a tissue. So this is also a tissue. Moreover, they both agree with regards to what the tissue is. So I'm going to know that P also knows from this that this object is going to be a tissue. And then, moreover, P knows that whenever something is arguably a tumor according to T, then it's going to be the result of a tumor process according to itself. So he's going to know that there is some tumor process going on associated to this instance and ultimately associated to this patient. So with this, we have basically a full setup of standpoint logic. This is what a model looks like in standpoint logic. You're going to have a collection of interpretations, and you're going to be able to establish bridges between interpretations. So in a way, this allows you to establish tight interactions between the different interpretations, but you still don't force them to be consistent between them, okay? So this is the main idea. Yeah, then we can infer also more the fact that this is a process, etc.
Can you just repeat where do you see the possible world as the state P? Is each line is a possible world? Each
line is a precessific, so we call them precessifications, but they are akin to possible worlds in model logic. So it's the same thing. So each I is a possible interpretation. And then what you have is that these possible interpretations are going to belong to different standpoints, okay? So for example, here, pi prime belongs to T, but it also belongs to S, okay? Because by saying that T inherits everything from S, you make it a subset of S.
Yes, so implicitly it is here you consider an indistinguishable relation which is an equivalence relation between all the sets.
Yeah.
Totally equivalent to S5 logic.
Not really, because what you don't have, so what you don't have is reflexivity, okay?
Only reflexivity,
the only
not
thing.
introspection. Okay. Yeah, okay, I understand.
Okay. So this is the first intuition. Let's go a little bit formal to the syntax and semantics. So to give you the syntax and semantics, we're going to stay with first order model logic. And the whole idea behind going for first order model logic is that for knowledge integration, so very often we're going to see model logics being explained in propositional logic, but for knowledge integration, this is very often insufficient. So what we are going to be doing is we explain the framework for the first order case, and then we are going to be looking at specific fragments of first order logic and specifically decidable fragments of first order logic and showing the decidability of standpoint logic for these fragments. So we say in the general case of first order model logic, and we're going to have these signatures that are very natural. So we're going to have a set of predicates, a set of constants, and the only new thing is a set of standpoints. Our formulas are also going to be built in a natural way. So I'm going to have the usual connectives and in addition the box operator, okay? Now the box operator is going to read as is unequivocal according to E that phi holds. As usual, I'm going to have the dual diamond operator that's going to read as is conceivable according to E that phi. And then in addition, we can not only use these standpoint symbols in the model operators, but we can actually build expressions of standpoints, okay? So we can use, for example, the union of standpoints. It's going to read as is unequivocal according to both E and E prime that phi. Or the intersection, that's going to refer actually to the fusion of E and E prime. And then finally, we can have some sort of like syntactic sugar, which are these subsumption or sharper than operators that I showed you before to establish the hierarchies, which can actually be encoded just with this formula. Basically, we say that the difference of the standpoints is empty. But yeah, we can use this to establish that E inherits or extends E prime. So this for the syntax, and now for the semantics, what we're gonna have is a relation of semantics. So this is our structure. What we have here is, first of all, a domain of individuals, since we have first of the logic, and we're gonna have yeah, we're gonna have the unique domain assumption. You don't call it unique domain assumption, but basically all the interpretations will share a domain. Then we're gonna have this set pi here, which is your set of possible worlds in model logic, okay? And then the main difference with usual cryptosemantics is here in this third place, where we have this function sigma. Sigma is gonna map every standpoint label to a subset of the worlds. And instead, in the usual multi-modal logic case, what you would have here is a set of relations over the set of worlds. And in fact, this difference, this simplified semantics, is what brings about all the good computational properties of the framework down the line. And it comes at the cost of not being able to express the mental state of agents. So again, this is a reminder that, like, we often talk about standpoint logic as in a logic of perspectives of standpoints. So these are explicit, you are not modeling agents themselves. And basically, the framework is actually applicable in a lot of different scenarios of multi-agent systems, but it's going to be applicable in those scenarios that don't require modeling the mental state of the agents. And yeah, finally, we have gamma, which is basically mapping each world to a first order interpretation. So to give you an example of a model, we may have these two domain elements. We may have these three different worlds. So we can map them here as before. And then I may say that the standpoint R is a set of pi 1 and pi 2. So these two here. I may have another standpoint B, which is pi 2 and pi 3. We have it here. And then we always have the standpoint star, which is the full set of precessification. So this is going to be the equivalence relation, actually. And then, yeah, gamma just gives the first order interpretation. So then the satisfaction, the only interesting part, let's say, is to look at the satisfaction of the model operators. You know, everything. Thank you very much. So what's interesting basically is the satisfaction of the model operators, but that's also very natural for first order logic. So basically, I'm going to say that box B, P of A is true if P of A is true in all the precessifications of B, so in all the worlds. So basically, we need to make, so since this element is A, is a constant A, then P of A should be true in both pi 2 and pi 3. So in this way, this is satisfied.
So the meaning of the formula in the middle is for all model, for all interpretation, for all valuation in your model, for all accessible world, the predicate PA is true. It means here in your formalism that, for instance, in P2, you will have P, and in P3, you will have also PA, which is true in those possible worlds.
Yeah, basically, I think I'm understanding you well. So like the idea here, the only thing that changes basically with a usual model framework is that in a model framework, the box is interpreted as departing from your current point, you need all the accessible points to satisfy your formula. In this case, you don't need to focus on any current point. The only thing that you're going to check is that the formula is satisfied in all the points that belong to the standpoint that you're talking about. Okay, and this is why we cannot model the internal state of the agents, because you can access this from anywhere in the model. Okay, nice. Okay, very nice, very nice.
So you replace the accessible state by the actual set of states of the standpoint in the end.
So you don't really need a pointed model, basically.
You don't have the pointed model, you replace it by this set of your set of, okay?
Yes, exactly, exactly. And then the diamond is as usual, is you just need the formula to be satisfied in one of the worlds. Okay, so this is very nice. So this is the syntax and semantics of the language. And now let's look at what have we been doing with it. So yeah, so of course, we've been doing some work on different decidable fragments of standpoint of first order standpoint logic. And basically, I'm gonna try to navigate you through the main results that we have. I have some additional slides with more technical results showing a bit the proof techniques that we've used for some things. So you feel free to ask me if you are interested on that. So, okay, so for this decidability and complexity landscape, the first thing is, of course, this model can be rewritten into a usual Kripke style model quite easily. So we can borrow, for example, decidability results, etc. But we can very often establish tighter results for standpoint logic. Okay, it's better behaved. So as with model logic, the main factors in the decidability and the complexity of the fragments are, of course, the complexity of the fragment itself, but then it's going to be the number of free variables under the scope of the model operators that I have. So we're going to be looking mostly at two fragments today. First of all, we're going to be talking about the sentential fragment, which doesn't allow any free variables inside of the scope of the model operator. This is very easy to handle and well behaved. So for you to have an intuition, it behaves a bit in the same way as you just couple the propositional framework with it. Basically, the model infrastructure doesn't really interact with the underlying fragment that you have because you are not allowing for these free variables. So you can really treat it as if it was propositional, and then in every of the worlds, then you need to have like a reasoner for the base language, roughly. So the complexity, one should expect that you can like directly take the greatest complexity, be that of the standpoint framework and the model system underneath. This is very, okay, so this is nice because on the one hand, what we have is, well, perhaps I'm going to talk a bit more in detail later when we go for it. But then the other fragment that we're going to be looking at is a monodic fragment. The monodic fragments allows a single free variable inside of the scope of the model operators. Okay, and this is full standpoint logic is still very well behaved. So for example, to give you an intuition, we are going to be showing results for this, but this translates when you are using a description logic as the underlying language instead of the first order logic. It means that you can use model operators both at the axiom and at the concept level. And usually for most multimodal frameworks, this involves an explosion a bit in the complexity. It's harder to deal with. But for standpoint logic, we can preserve, for example, for EL, we can preserve the polynomiality of the framework with this model infrastructure. The proofs are a bit more involved, however. And yeah, we've been also working with LTL, where we can also show that we preserve the complexity of the baseline. Then we have beyond monodic fragments. So for example, allowing two free variables inside of the scope of the model operators. We have not worked on this yet. Very often model logics allowing more than two free variables go undecidable. We would expect that, for example, for description logics, we definitely can keep decidability in certain settings. And we actually think that we can establish possibly decent bounds on the complexity because of the properties of standpoint logic. There are some additional things that play a role in the complexity. So this is the main factor, but then we are going to be playing with some tweaks for the language. So for example, sometimes we can allow for emptiness of standpoints. So when we use, for example, the sentential fragment that is well behaved, we allow for empty standpoints, and we allow for the full set of combinations. This can actually not be allowed if we want to keep the polynomiality of EL, because we can actually encode disjunction with this. So this is forbidden there. And similar with combination operators. They must be disallowed for EL, and they are also disallowed for LTL. If we want to keep the complexity, of course, if we don't care to have a compound complexity, we could allow. So let's go a bit more in detail with this. So for the sentential fragment, again, the idea is that we do not allow for full variables inside of the scope of the model operators. And then what that gives us is a small model property that tells us that we need only as many worlds as the size of the formula that we have. With this, what we can do is we can basically establish an equisatisfiable translation from the standpoint version of the language into the base language. So with this translation is equisatisfiable and is polynomial. So that gives us basically it gives us satisfiability results for free for a variety of languages.
Yeah, excuse me, my stupid question, but what is the specification?
It's a world. You can assume that it's a world. So like the reason for using pre-specifications is that in the supervaluationist theory where this whole thing comes from, they differentiate between worlds that implement states of affairs they say that they are different from pre-specifications which actually model interpretations of the language. But
is it a set of words where the formula phi is true or?
Yeah.
Oh, okay.
So here would be, yeah, exactly. So this small model property what tells you is that if you have a first order standpoint, sentential standpoint logic formula, you check the size of this formula and you know that this is going to be satisfiable in a model of at most that size many worlds.
And quick question, do you use this theorem to build a canonical model or?
No, we actually don't use canonical models in this case because what we use this theorem for is to build a translation, basically.
Yeah, okay.
So I can show you the translation later on. I don't want to take over the whole presentation for it, but we can talk a bit about it later because actually this translation is good because it allows us to show the completeness and the results for all the fragments that are compatible with the translation. But it's also nice because it can be very easily implemented. And since the translation brings you, which this is basically the next slide. No? So like with the translation, we can show, for example, that all these fragments stay at the base complexity. So we can add standpoints for free, sentential standpoints for free. But the other nice part of it is that indeed, so let me go straight here. The translation what allows us is to be able to use already existing reasoners because the translation is going to bring you from the model version to the model-free version. So, for example, we have adapted this translation to the syntax of OWL. And what this means is that just by implementing this, we can then throw it into an efficient reasoner and we can get basically stamping reasoner at a very low cost, okay? And reasonably optimized, much better than if we had to develop our own reasoner from scratch. Yeah. In addition to this, we've also been developing Gensen-style nested sequence calculus, which is nice. On the other hand, we developed this only for the propositional case in principle. This is nice because it's explainable, okay? So like we have control model extraction and we have proofs to show the validity of the formula. So yeah, so this is very nice. And yeah, as I was saying, we will hopefully have our first reasoner very soon. So we're planning to submit the first prototype to FOSL this year and then do some large scale testing with it to see how resilient it is. But then we can move on finally to the monodic fragment. So if we go back to our example at the very beginning of the talk, this example, it was phrased in first order logic, but it's actually expressible in EL. And however, the sentential fragment was not good enough because when I was saying that something that was a tissue according to this standpoint is also a tumor according to this other standpoint, for this we require to have free variables, okay? So we require the monodic fragment. And this is where we are having like reasonably So the proofs are a bit more involved, but in most cases, one would have like substantial increase in complexity. And however, for sample logic, we were able to show that, for instance, for EL, we can keep the complexity of the base language. So for this, what we provided was a Tableau-based algorithm that's based, so basically it exploits techniques of quasi-models, which are often used for higher order model logics. But it has to be adjusted so we can actually show that we stay polynomial. And this becomes a bit more delicate. So as I was saying, for example, we cannot allow for empty standpoints. This turns the language into NP hard, and little introductions will make us lose the polynomiality. With regards to reasoning on this side, we've also been working recently on a subsumption calculus, materialization calculus for standpoint EL, which basically it has deduction rules based on data log, and it will also give us the possibility to have, so in principle, we already have a prototype for a reasoner, and now we need to go a bit into optimization to make it perform a bit more efficiently. But basically, this gives us tools to start going for more applied use cases with sample logic. And then finally, these whole strategies that we've been looking at, the nice thing about the techniques that we've been looking at for the sentential standpoint case and also for the monodic standpoint case is that they are nicely transferable to different base languages that we may want to use, okay? So something that we deal with in KR is that depending on the area of application, we're going to be using different languages. And something that's really becoming quite clear to us is that we can reuse the techniques quite straightforwardly between different languages. So, for example, this version of sample logic together with LTL is the product of a collaboration that started last year in KR, actually, with Nicola Girante, who talked to us after the presentation, because indeed for LTL they do model how different systems behave over time, and then whenever they need to deal with multi-agent systems, they may have completely different specifications, and they may need to model how do they interact between them. So using a similar strategy to what we use for EL, we were able to show that we can also preserve the B-space complexity for standpoint linear temporal logic. So we also have a Tableau-based algorithm. And the nice thing about this as well is that, so Nicola has been working on a SAT-based reasoner for LTL. But basically what it does is it gradually builds a Tableau, and it sends its partial builds to a SAT solver, okay? Because SAT solvers are actually very efficient. And by doing this, they actually manage to have like state-of-the-art performance. And something that is quite nice about this is that, of course, whenever they do this translation of the partial Tableau-based algorithm, they use, usually in the general setting, they will use it for a propositional language. But using our previous translations for sentential standpoint logic, which they are not restricted to sentential standpoint logic. They are just, you just need to know how many words you need, which you know with these trees. You can actually basically use the translations and throw them into the reasoner and have reasoning support for sample logic, again, almost for free. So this is very nice, and this is going to be very soon work to be published. But yeah, as a conclusion for the overall talk, I hope I have been able to convince you that sample logics are very well behaved model logics that are quite useful for a lot of settings in which we may want to model the behavior of multi-agent systems, but we don't need to model like the intrinsic mental state of the agents that are involved in the system. So we have like already well-developed techniques for sentential and monodic fragments, and we do have like ways to tweak ways to slightly restrict the expressivity of the base language in order to preserve the good complexity bounds whenever we want to have like variant type languages. We are going to be exploring the case of more expressive fragments, so basically going beyond the monodic, because we do believe that we can still have interesting results on this area. But something that we are also interested on at the moment is, first of all, to push the area of the implementations to be able to have solid systems for this. But also we are interested into introducing some non-monotonic flavors into standpoint logic. So there's going to be many cases in which we may want to perform some softer merges than the ones that the current combination operators allow for. And we have already been discussing with, for example, with Kai Sauerwald in Germany and with other colleagues. We have some ideas basically, but this is kind of an exciting and open area of research for us at the moment. And yeah, this is pretty much it. So yeah, thank you very much for listening. Feel free to ask me any questions. Very last note, we are organizing a workshop on knowledge diversity that's going to be co-located with KR this summer. So the topic is quite broad. We are going to be organizing it with certain basic here in France and Rafael Peñaloza in Italy. So for topics of interest, we have like anything related to knowledge diversity, from multi-perspective frameworks to belief aggregation to uncertainty in knowledge diverse systems, etc. So if you are interested, please go ahead and submit. It would be lovely to see any of you in Greece. So yeah.
Thank you. Thank you very much. Hi.